Hello everyone, in this video we're going to discuss work as it relates to energy, and by the end of the video you should be able to feel confident calculating the work of a given situation. So this is what we have for our work equation here. The work, which we define as W, equals the parallel force to distance, which also equals the force distance times cosine of theta. So what does that actually mean? If, let's say, we have a box and a force is being applied to it at this angle, and let's say the block travels this distance. The work is basically how much force is applied over this distance, and that's what defines the work. So this parallel part of the force would be this. It's the parallel force to the distance, which also, if we want to find this component of force, equals cosine of the angle that the force makes with the distance. So that's how we're getting this equation. So something to note is the units of this is going to be a Newton times meters, which equals a kilogram meters per second squared times a meter, which if we multiply these meters together, we'll end up getting kilograms meters squared per second squared, which equals a joule. So it's also a unit of energy, just like kinetic energy would be. So this is also going to be a scalar quantity, but work can be either positive or negative, and we'll show a few scenarios down here. So let's say we have a box that is applied a force like this and travels a distance like this. In this case, the work is going to be positive because force and distance are in the same direction. But if we have a different box and the force is being applied in this direction but the distance is this direction, in this case the work is going to be negative, because if we did FD cosine of theta, this theta would equal 180 degrees, and so cosine of theta would be equal to -1, and so you would have a negative work. And now let's say we have a box that's being pulled with a force upwards and it travels this distance. Well, in this case, the work due to this force is going to be equal to 0, because the force is not applying any force in the direction of motion. So in this case, the work will be 0. And so one last thing to discuss, if you get a graph of, let's just do it up here. If you have a graph of force times the distance, let's say it just looks something like this, right? If you wanted to find the work, we know the work equals the force times the distance. So as long as this force is the parallel force to distance, the area under the curve will be equal to the work done over this certain distance. So if you're ever given a graph, you can find the work graphically by finding the area. Alright, so let's do a couple examples relating to work here. So we have Bob picks up an 8 kilogram box, a distance of 1.5 meters, and brings it to his house that's 5 meters at a constant speed horizontally. He then places the box back down 0.5 meters. How much work does Bob do on the box over this entire situation? So let's write out what we have. So we know the mass of the box is 8 kilograms. So we know the first distance is picking up the box 1.5 meters. He then travels a second distance of 10 meters and then places the box back down 0.5 meters. So we need to figure out what the total work over the situation is. But you'll notice that we can't just add up these distances and say that the force is going to apply on these equally, because different things are happening. So let's draw what's actually happening. So first, we have the box, and it's being picked up with a force, applying this force upwards. And it's traveling this distance, or we'll just call it d1. So that's the first situation. And so now the box is up here. And so now Bob is walking with this box this direction, a distance of d2. But the force that he's applying is still going to be just holding the box upwards, that normal force. There's no force actually pushing this box this way. So the force is only up and down as the box is moving at a constant speed of force gravity and the applied or normal force that's holding this box up. And then we have placing the box back down. So now the box is over here, and it's going down 0.5 meters. But we're trying to find how much work does Bob do on the box. So the force gravity is pulling this box down, but Bob is still applying this force upwards. So the force is up, but the distance is down. This equals d3. So if we want to, let's do it for each situation. So we have work from the first distance is going to be the force that Bob is applying times the distance, and we know these are in the same direction. So if we have cosine of theta, theta is 0, so this cosine will just be 1. But what is this force going to be? So if we draw our little free body diagram for this first situation, we have the force due to gravity of the box and the force applied from Bob that lifts this box upwards. But they're going to be equal because he's lifting the box up. Right, and we can assume he's lifting it up at like a constant average speed so that these forces will be equal. So this force applied here is just going to equal the force due to gravity. So we know this will equal the force due to gravity times distance, and the force due to gravity is just simply the mass times gravity times distance. And so that'll be the work that he does during the first time. So we can plug in the variables because we have all these variables. As the mass is 8, gravity is 9.8, and the distance he travels is 1.5. So this is 117.6 joules. And so now let's talk about situation 2. So in this case, we have this angle equal to 90 degrees between the force and the distance. And cosine of 90 degrees is just equal to 0. So the work along this path is just going to be equal to 0. Because Bob is not applying a force, he's just walking with the box, and the force is actually happening like as he's like speeding up and slowing down under his feet. So he's not actually applying any work to the box as he walks with it. Okay, and then for the third situation, now when Bob is holding this box, you may think the force is in the same direction, but what's actually bringing the box down is the force due to gravity. He's holding the box from falling. He's bringing that box downward. So the force is actually in the opposite direction, and the work on the box is going to be negative because that cosine theta will be -1. So if we have this force applied times distance cosine of theta, this cosine of theta is going to equal cosine of 180 degrees, which equals -1. So this will equal a negative force applied times distance. And in this case, the force applied will equal the force due to gravity. So we'll have a negative mg for this situation as well. And we can plug in the values. So the mass is 8, then we have 9.8, and then a distance of 0.5. So if we plug that into a calculator, we'll get negative 39.2. And so now we want to find the total work. So we can just simply add up all the works. And so we can plug in what we got. So we got 117. The first one, we know the second work was 0, and we can subtract that last work. And so the final work will be 78.4. And so you can notice that it only depends on this initial and final position of the box relative to the vertical, because he's only doing forces applied in the vertical direction. Alright, let's do one last example here. So we have Bob pulls a 15 kilogram box up a rough incline with an angle of 20 degrees from the horizontal. He applies a force of 300 newtons parallel to the incline and travels 9 meters. The coefficient of friction is 0.37. We want to find what is the work done by friction and what is the work done by gravity. So let's write out what we have first. So we know the mass of the block is 15 kilograms. The angle that the incline makes is 20 degrees. The force applied is 300 newtons. We know the coefficient of friction, and since it's a sliding box, we know it'll be kinetic friction, is 0.37. And the distance he travels is 9 meters. So if we draw our incline here, it'll have an angle of 20 degrees, and the box is going to be like this, and it's going to be pulled up this incline here. That'll be the force applied. Okay, so let's first draw out kind of the free body diagram on this box here. So there'll still be a force due to gravity coming down, a force normal coming off of it, and then we know there's gravity because it says there's, we know there's friction because it says there's a coefficient of friction. So the friction will be always in this opposite direction of motion. And so we know that this box travels a distance of d, and that's 9 meters. So we want to know what is the work done by friction. So we know what work equals. So the work equals the force times the distance cosine of theta. So in this case, we need to figure out what do we need for the work of friction. So we know it'll be the force due to friction that's causing the work. The distance will be the same because it's how much the box is moving. Cosine of this theta, I'm going to call theta f. It's the theta that is related to the friction, force, and motion. So since friction is in this opposite direction of the distance, because we know the distance will be that way, as it's pulled up the incline, this cosine of theta will go to -1 because it's 180 degrees. And when you're working with friction, it's always going to be 180 degrees from where motion is. So we can simplify this to the work equals the force due to friction times the distance. Now all we need now is the force due to friction. But we're not given that, so we're going to have to use our force equations. So we know what force friction equals in terms of other variables as the coefficient of friction times the normal force times distance. So now we just need the normal force. So we can use our y equations here. So if we look in the y direction, and we can set our y direction to be at this angle here, so that we'll have our force normal equals this Fg in the y direction. And so if we want to solve what out this is, we're going to have this angle here, which equals theta, is also going to equal to 20. So we're going to have this cosine define this y. And so we have Fg times cosine theta because of where the angle is off the horizontal. And then we know Fg is equal to mg cosine of theta. And so now we know what Fn is, and we have all these other variables, so we can plug this back into the work by friction. And so now we have everything to solve the equation, so we can just plug in the variables we're given. So 0.37, the mass is 15, gravity is 9.8, cosine of 20, and the distance is 9 meters. So after we plug all that in, we'll get the work by friction is a -460 joules. And so friction work will pretty much always be negative because it's slowing down, or it's in the opposite direction that the box is trying to move. So the box is trying to move that distance, but the friction is doing work against the box moving. So now we need to know what is the work done by Earth's gravity. So I'm going to scroll down a little bit here. But if we want the work due to gravity, then we're just going to use Fg is going to be what's causing the force times d cosine of this theta, and I'll just say theta g, right? So we could try to find the angle that's between the force due to gravity and the force applied, which wouldn't be too difficult. We could add 20 to 90, but we could also use the version of the work equation where the force is parallel to the distance. And we know the force that's going to be parallel to the distance is going to be that Fg in the x direction. So then we can plug in our work due to gravity's Fgx times d. But we know that since Fgx is in this opposite direction of the motion, it'll be a negative Fgx times d. And so now we can find what Fgx is. which is just the mass times gravity, because that's force due to gravity. But then the angle from this incline is cosine, or it's going to be sine because it's off the parallel. So it'll be sine of theta. And then times the distance. And so now this theta is still this 20 from up here, and we didn't have to find any weird angles, and now we can plug in all the values that were given. Sine of 20 times the distance of 9. And so the work due to gravity is going to be a negative 452.5 joules. And so since this box was sliding up the hill, the work is doing negative work, but if the box is sliding down the hill, the gravity would be doing positive work. So that's where the sign comes in. So really the main thing to know here for work is that we know the work equation, we just have to find what force is doing the work and then solve for that force using force balance equations that we learned about in Unit 2 of Physics. Alright, so leave your questions down below, and make sure to stick around for next video where we'll talk about the work energy theorem and relate the change in kinetic energy to the work. Alright, thanks for watching.